So thank you to Adrian and Trent who are joining me for this presentation of an Ethereum client architecture. Hello and welcome to Adrian and Trent, and to whoever's watching this at a later point in time. And I'm already looking at my slides and seeing the first lie, which is the date on that slide. So the date is when I originally presented and not the day it is now. So yeah, there are likely to be mistakes and errors. So first, before I get into any details, I want to make a warning. And my warning is similar to the Latin phrase in vino veritas. So I think if Caesar was a coder, he'd say in codo veritas. And that is to say that in code there's truth. So not only in wine is there truth, but also in code. And so what I'm presenting to you is a high-level architecture that is based on what I've seen a number of different Ethereum clients do, but it's an architecture diagram and a presentation of architecture. If you really want to know what an Ethereum client does, go to GitHub and find one and read the code. So let's start with a question. What do you think an Ethereum client is? So Adrian, Trent, you've had at least a couple of days at Consensus and have looked at Ethereum. What do you think an Ethereum client is? What have people told you that an Ethereum client is, either by analogy or whatever? And there's no wrong answers.
So there's lots of wrong answers.
Hey, I'll start with one. So one of the things an Ethereum client does is run the node that mines blocks and verifies transactions, or verifies blocks.
Yep. And so what's Ethereum?
I'll give that one a crack, eh? It's probably my turn. So Ethereum is a distributed system for maintenance of data and arbitrary code execution.
Yep, cool. Those match up to lots of things that I have on the next slide. So I like those words. We can keep moving. So some things that I've heard tossed around: a distributed ledger. So it stores a series of transactions in a distributed database. I guess thought of maybe as a database. There's a peer-to-peer network sort of sitting there to help make it all work. And another magic word, the phrase that people like, is a distributed computer. So I hopefully will, with some of those concepts, we'll flesh out some of that as we go through things. The other thing to think about is the types of clients that are sitting out there. And so these are loosely used terms that are used to think about Ethereum clients. So moving from a light client to a full node, I guess the full archive node and mining pools. And so these are some labels that are used to think about Ethereum clients and are not a canonical list of things. They're not strongly defined, but I'll be referring back to them later. And there are often actually more ways that you would configure your client to be running. So it's probably a Go Ethereum client. You could configure it to be running as a light client, or as a full node, or as a full archive node. So with a bunch of different configuration parameters. Okay, so as I go into thinking about the overall architecture of Ethereum clients, there's going to be some foundational things that we'll need to cover. And so I'll start with some of those. And then I'll start to zoom back out and then dive back into some actual more detail again. So some of the foundational bits that Ethereum is really heavily built on. First is two core technologies: the idea of RLP and a Patricia Merkle Tree. So RLP stands for recursive length prefix, and it's an encoding format that's used to be able to encode arbitrary nested arrays of binary data. And it's the main encoding format used in Ethereum. And so you'll see The yellow paper talks about RLP all over the place. We have the data is stored as RLP. The network, peer-to-peer network, dev P2P, is actually built on top of a layer called RLPX, which uses RLP to send the packets across the network. So RLP is actually everywhere in Ethereum. Tree. So the tree word, and you'll notice that I'm laying my case for how it should be pronounced as tree, not try, and is originally very clearly was created from the middle words of retrieval, and is a fast way of storing things. People often will say try instead of tree because you end up using it in the context of the word tree as well, and so you have a tree, and people like saying a try tree to just sort of disambiguate, but yeah. So that's a tree. And a Merkle tree is, I guess, another sort of core concept that sits behind blockchain. The idea with a Merkle tree is it's a data structure, which is a tree, and it's composed of hashing, sort of a tree of nested hashing. So if you look at the bottom node level there in that diagram, you've got a bunch of data blocks sitting there. So L1 to 4 are bits of data. The layer above that, you can see that you are storing within your Patricia Merkle tree hashes of each of those blocks, with the sort of key pointer to that being another hash. And so then you sort of build up that each level in the tree is pointing to a hash of the nodes below the tree. And so you can sort of see that with the second level of the tree has hashes of hash 00 and hash 01 as what it's storing. And then the top level has a hash of the hash 0 and hash 1. And so this is actually the foundational thing behind blockchains. And so you can see that the top level hash, it's built on everything below it. And so any change to any other node would then break that hash, and so thus be breaking the tree. So a tree, and this is a tree, or a tree, and it's a efficient way of storing data. And in this particular case, we can see that there's 7 different words that are being stored in this tree as a dictionary, and the tree is a really efficient way for minimizing the number of bytes that need to be used to store all of these words. And so instead of having to store the whole word Romain, Romanus, Romulus, you can see that it's able to just store the shared paths through that and the end final nodes. So you can see that Romulus, if you look at that, the R at the top, then the OM, and then the ULS is stored in that final leaf node. So that's a tree. A Patricia Merkle tree is then a tree structure, a tree, storing the Patricia Merkle, so the Merkle hashes. And so it's then an efficient structure for storing a Merkle hashing sort of structure that's there. And so we can see at the very bottom there, we've got the data that's being stored with the fragments of the hashes sort of moving back up that tree. So that's our high level what a Patricia Merkle tree looks like. So putting that all together, you get a Patricia Merkle tree of RLP, and that's what's being stored in the world state of our blockchain, of the Ethereum client. It's being stored sort of Patricia Merkle trees of RLP are then being stored everywhere in an Ethereum client. So we've sort of been lost in the details a little bit. I'm going to zoom all the way back out and give us the big picture. And that's our architecture of an Ethereum client, and we're all done. No, not quite. I'll go into some of the details. So what I'm going to do now is, you can see that from a high level, we've got the JSON RPC, and the request will come in through the JSON RPC. So that's what's exposed from a client to the outside world. Come through, it'll go through and create some transactions and do some work using the Ethereum core, and then do some storage of that information. As a part of that JSON RPC, it might need to sign transactions and do some work with digital signatures, and that would go through the wallet to do that, to get access to their account. As a part of creating that transaction, you're going to want to push it off to the networking layer so that it can be distributed throughout the network. So let's dive into that into some more detail, having done the really high level. And I'm going to go through each of the different parts. You can sort of see on this diagram, there's a number of levels of boxes. I'm at least going to go through every one of the top level boxes and briefly cover some of the next level down as well. So our JSON RPC is the first box that we'll look at. So it's the entry point into the client and how people interact with it, how your dApps interact with the Ethereum client. Provides a really broad API. So it gives hooks into the management of your client. It gives the ability to see some of the things about the network and do queries about it. You can then start to look at some of the blockchain, maybe do some interaction with some of the sub-protocols, and clearly that's also how you do the things like create transactions and post them to the blockchain. Our next box is the Ethereum core. Can be thought of maybe as a state machine and in some ways, or often thought of like a database instance. So if you think about a database for old school relational database sort of people, you think about the storage and then the sort of running process that's there to support things. The running processes, you think about it and call them the database instances. So that's kind of the Ethereum core. And so its job is doing things like processing blocks, coming to consensus, so using the consensus algorithms, and doing sort of some of the, maybe in like a model view controller type framework, helping to be the controller. So taking things in from the network, does the synchronization of the blocks that might be coming in from the network and puts them into maybe a transaction pool, and then puts them into maybe do some block processing and put them across then into the storage. So it's kind of the Ethereum core, that's where it sits. The networking layer is implemented using the Dev P2P communication stack, which is only really sort of specified as a part of Ethereum. And so you'll find you won't find any mention of Dev P2P apart from in the context of Ethereum. So Dev P2P is a P2P protocol based around RLP encoded messages. I'm going to do some details of this in the next couple of slides, and there's another talk which I've got which covers this in more detail. And so I undoubtedly will be creating another presentation of that in the next couple of days, and Trent and Adrian will be hearing that, I think, the guinea pigs again, and it'll be available for wider distribution as well. So let me go from the top. So the discovery. So the discovery protocol is used for helping to discover other nodes in the network. It starts by sending a message to a list of boot nodes. In most of the clients, those list of boot nodes is a hard-coded list. And so there's a set of about 5 boot nodes in Ethereum that are really quite important to the whole network and to adding new clients to the network, which if they went down, Ethereum would probably struggle to have people adding new nodes, brand new nodes to it. That said, that bootstrapping sort of process, clients, the clients that do have that static list of 5 nodes also then cache the results that they get. And so they don't actually need to go through the bootstrapping process on a regular basis. It's sort of a first thing that they do, and then they remember that and store that. The discovery process is based on the Kademlia peer-to-peer distributed hash table, which is sort of well-defined in a paper. The discovery process uses about half of the Kademlia sort of work. So the Kademlia sort of breaks down into 2 parts of how do you discover and maintain a network of peers, and then it also talks about how you store data in those peers and retrieve data from the peers. So the actual Ethereum implementation does not use any of the distributed hash table features of the Kademlia protocol. It only uses the network sort of discovery and management sort of side. So the discovery side, also another point to make is that this runs on top of UDP, where the rest of the protocol then runs on top of TCP. After having done some discovery, there's actually a sort of step that's sort of missing here, which is that there will be, sort of independent of that UDP discovery process, there's going to be a session sort of initialization process that needs to happen on the actual TCP communications happening between nodes. Having done that initial beginning of that session initialization, there's some sub-protocol negotiation. So that job of the sub-protocol negotiation is to work out which sub-protocols are supported. So I can talk more about that in the next talk. So a lot more details. I know I'm not answering many questions, but giving a high level. But the first thing, one of the things that happens is our dev P2P process is working out which sub-protocols are supported. And so examples of the sub-protocols that can be supported, one of the key ones is the ETH sub-protocol. And so the ETH sub-protocol is the most important one and sort of the central one for everything. And that's how blocks and transactions and sort of the related metadata are shared throughout the peer-to-peer network and shared between Ethereum clients. So a miner will use the ETH protocol when they produce a new block and they've mined it, they'll send it out and kind of promiscuously share that. A new client, when it's coming online, will use the ETH protocol to get its data in most situations. There's some other similar protocols that are used for maybe doing fast syncing and more efficient way of pulling down a large amount of blocks. But the ETH protocol can be used to support everything that you want to do there. So some of the other sub-protocols are Whisper. So Whisper is not currently well implemented within clients, so it's there in Geth, but most people don't actually have it turned on. So if you sort of start up an Ethereum client and start looking at the sub-protocols that people say that they support, most people actually don't have Whisper turned on. So Whisper, it's a privacy layer. It allows sending secure messages between peers, and it does it without writing to the blockchain. So if you want to send messages, you could, I think the examples and use cases that are talked about is maybe a chat system. Maybe you want to implement the next version of Telegram, but do it using peer-to-peer. And over Ethereum, you could do it with Whisper.
So Rob, just quickly, the JSON RPC allows the DApp full access to that?
Yes. So some of the JSON RPC, some of the clients that support Whisper, then expose that through the JSON RPC.
Right.
Cool. So Swarm. Swarm is a decentralized file system. Another decentralized file system built on top of Ethereum that's probably got more mind share and is probably getting more and more maturity is IPFS. But Swarm is another way of doing that is done through the great sort of P2P and Ethereum clients. And there's more. So it's a extensible protocol, and so you can multiplex multiple different sub protocols on top of the P2P protocol. You just need to make sure that in the sub protocol negotiation phase that you publish which protocols you support, and then if another client supports those sub protocols as well, you can start sending messages to that client. So that's the high level of networking. There's lots more details that we can dive into, but not in this talk. Unless there's questions now. So I will pause. Do you have any questions about networking? And no is a perfectly good answer, and I'm going to go with no. So moving then across to the left-hand side of the diagram, we've got the storage side. So as I mentioned before, the storage is all about Patricia Merkle trees of RLP encoded data. And so the storage in terms of most clients, so if we look at the things that are sitting there, you've got your code storage, you've got your account storage, you've got your world state, and the blockchain. So the world state, account storage, and code storage, the way that they work are all specified in the yellow paper as Patricia Merkle trees of RLP encoded data quite specifically, and done that way because the hashes of those data items are then referred to from the blockchain. And so the actual idea that you're using Patricia Merkle trees of RLP, you actually, implementers are all very much sort of pushed and encouraged down that direction, because that's what you need to be referencing back out to. So most of the clients that are available are using just simple key value stores for storing the data inside these items, and there's often level DB is being used behind the scenes. So the use of a key value store or level DB is not specified anywhere, but the fact of it is that the things that are specified and the access paths and the way that you need to work with things very much lead towards the use of a key value database. So sitting on top of our storage, there's the idea of a wallet. So I guess the wallet in a Ethereum client, it's a term that people will probably be familiar with, but is not what people kind of think of. Like actually saying Ethereum client, a wallet actually doesn't do quite what you think. So wallet doesn't hold money. Your wallet actually holds your keys. So maybe it's a key purse, maybe it would be a nice way of thinking about it. So the job of your wallet is to store private keys. And we talk about that's what the responsibility of the wallet is in an Ethereum client. So I'm going to sort of hop back out and think about how things interact a little bit. So if we look at the Ethereum core to the Ethereum network, there's all these transactions that are happening and that might be coming in from another node, or blocks might be coming through. those are then going to get pushed in through to the synchronizer. So the idea is that the ETH subprotocol will have, you can have blocks coming in across through the ETH subprotocol. They would then need to get passed through to the synchronizer. Synchronizer will be then responsible for putting them into the transaction pool. From the transaction pool, the transactions would then go through the block processing system. And so the sort of nested things that are happening there is a block sort of comes in, you want to, I guess, validate that the block is a valid block and that it makes sense. The way that you do that is you're going to need to process the transactions and go through that, do that, executing the byte code inside those transactions, and do that using the Ethereum virtual machine. And that sort of idea that that's how blocks get processed and worked is, again, a pretty common sort of idea across the Ethereum clients. So that work of actually really processing blocks is going to be done as a part of, like I said, the processing blocks and creating blocks. So taking a series of transactions and putting them together and chaining them in a chain of transactions to form a block is going to happen. And a part of creating that block is done through the consensus sort of mechanism. So agreeing that a block is a valid block. So the ways that and algorithms that exist for doing that start with things like proof of work, or POW. So proof of work is you are doing some sort of cryptographic puzzle to prove that it works. The other algorithms that, if I just quickly cover them here, we'll go into a little bit of details now and before another talk, which is yet to be put together, which will be talking about the actual real details of these consensus mechanisms. So proof of POW, or proof of work, proof of stake, so proving that you've got some sort of stake or investment put aside, proof of authority, and then others and variants around the proof of authority in particular. So the proof of work algorithm talks about having some sort of hard to solve problem. And so the original proof of work that was there is the Bitcoin proof of work, or the most well-known sort of leader there is the Bitcoin one, where it's having generating a hash that finding the number to generate a hash that starts with a specified number of zeros at the beginning. And so that's a hard thing to solve in the first place. But then once you've got the solution for what it is, it's easy to verify that the solution is right. And that's kind of the way that the proof of work algorithms work, is there's some sort of hard to solve sum or cryptographic puzzle. Once you've got the solution, it's easy to verify that the solution is the right one. And so actually, if I flip back to the proof of work algorithm that is implemented within Ethereum is different to the Bitcoin one. It's been designed specifically to avoid and make it hard to compute by dedicated hardware, to make it so that people can't just build cheap mining rigs that solve it. Our next idea is proof of stake. So a set of validators take turns proposing and voting on the next block, and the weight of each vote depends on the size of its deposit. So this proof of stake is something that's coming sometime soon to Ethereum, although it's been coming sometime soon to Ethereum for extended period of time. So it's soon, anytime soon, where soon might be a week, a month, a year. The next algorithm or thing to think about is proof of authority. So having a set of authorities where authorities create new blocks and secure the blockchain, and some sort of sign off on by a majority of the authorities.
Now, Rob, doesn't that kind of break the distributed nature of the system? Or am I looking at this the wrong way?
Yes, it changes some of the distributed nature of it. Yes, and so it's moving it from some sort of complete distributed trust in everyone to, or needing to not have trust in people, to having a smaller set of trusted people, but the data is still distributed. So yeah, it does change the nature of the beast, and that's some of the criticism of some of the different consensus mechanisms are: is it still really a blockchain?
Mm.
If you start changing too much the way that the consensus is done.
Mm. Okay.
So some of the other consensus mechanisms are Raft, which is very guilty of changing that functioning. There's the series of Byzantine fault tolerant solutions, and one of the ones that has started taking mindshare in the Ethereum space is IBFT. Mainly because it's been implemented and shown to work pretty well. And so it's not perfect, but is a part of quorum and is sort of well specified. And so is expected to be something that the Pegasus group will be including as well. And then there's a bunch of other different consensus mechanisms. It's the flavor of the month for research is to say what kind of cool, funky consensus mechanism can I produce. Okay, so that's sort of getting to the end of that direction in the deep dive. I'm going to pull back up, and when I say deep, it's probably more maybe wading pool depth than really deep. So if we look again, this is the diagram of the high level overview of an Ethereum client. I can start to now talk back to the types of client that we had. And so we sort of look at that list of going from a light to a full archive node to a mining pool lead. We can have a look at how they would run in terms of a client and what parts of a client they'd be running. So a light client probably has the whole of the JSON RPC running, and then it's going to have no consensus sort of mechanisms, because it's going to defer all the consensus type work to other clients. So it's not going to be doing the proof of work. The synchronizer and transaction pool it probably still would have running, the ability to do some block processing work. A light node would not have any storage really of its own. It might have a little bit that's cached, but it's going to defer all the blocks to the networking layer. And so it's going to want to be using networking to essentially query other nodes. A light node probably doesn't actually respond to any requests for other information. And so I've got within the networking layer, it's sort of got partial implementations of much of the networking. And when I say partial implementations, it's partial parts of those implementations running. So again, this would be probably a Go Ethereum, for example, client that's running that just has lots of things, I guess, configured to be off.
So if you had a gap in this environment and you want to query the world state, it would effectively, the light client would act as a pass-through to a full node at that stage, or? Yep, that's right. And that's supported by the ETH protocol or something else?
Yeah, it'd be using the F protocol to help go off to the full node.
Cool.
And then a full node, in this world, it's going to verify blocks coming in from the network and maintain the current world state. So you can see that the world state is kind of a partial implementation, and it's probably not running any consensus mechanism. So it's depending on other nodes to do the work of the proof of work type implementation. A full archive node then differs from the full node by storing the world state and the full history of world states. So making it possible for you to go back and look at what was the world state at a particular block in the past. And so by nature, that's going to have a bunch more storage because it's going to need to have to keep all that historical information there rather than just the latest view. The next guy is a mining pool lead. And so the idea with this is that if you're running a mining pool, you probably actually have dedicated machines actually doing the mining work of solving the cryptographic puzzle, but you'd need to have something that's sitting in front of that actually talks to the Ethereum, the rest of the Ethereum protocol, and does the dev P2P, stores stuff, and you probably want to keep a fair bit of the history so that you can easily sort of verify maybe some reordering and that kind of thing. The main job though of this mining pool lead is to implement the consensus, and so you can see that's fully filled in for the first time, and as a part of that, and it's going to be taking transactions from the transaction pool, pushing them through the block processor, creating a potential block from that, a candidate block, then putting that candidate block through the consensus mechanism. And once it's said, okay, yep, we've got a solution to the proof of work for this candidate block, it's going to then publish that out through the ETH protocol and push that block out to the network. So again, the types of clients that we've just gone through, this is a nice kind of reference slide for you to look at in the future. We've already talked about everything that's here. And again, just for our reference, that's our full client that we've talked through. So this is the high-level architecture. You've got the JSON RPC, which is where your DApps interact with. That's going to take those requests, put them into the Ethereum core, probably pass them off to the networking layer. The networking layer is going to distribute it across to the other Ethereum clients. And then from there, it's going to come back into your Ethereum core and get stored. So to help us go through this just a little bit more, I'm going to take another couple of swings back around at this architecture. One way that we're going to quickly look at next is how Enterprise Ethereum looks at it. And I'm actually going to move very quickly through this diagram because there's better resources to look at it. And the copy of it into this presentation has left it not as high res as it could be. So essentially, you can see that if we look at down the bottom, there's the networking sort of layer. You've got the green dev P2P sort of sitting there. And this is talking about it in terms of, I guess, like a layered diagram. So that, I guess, in terms of people will talk about this as maybe the networking being a layer 0, the core blockchain being a layer 1, and then some of the things sitting on top of that maybe being a layer 2 type solution, and so on. So we can see here the core blockchain. Building on top of that, there's, I guess, the privacy sort of things that are sitting there. And then on top of that, you've got the JSON RPC layer that you can see. And once we start getting above that, there's the DApps and things that are interacting then with the application, with then a whole bunch of extra stuff that forms a part of the enterprise Ethereum spec. And I think the key things that if you're looking at enterprise Ethereum to sort of classify things as, and you want a high level, would be the permissioning, the privacy, and performance. And so the performance ends up being some of the private consensus mechanisms that are sitting there. And there's another way of looking at things, and it's always interesting within this kind of world to follow the money, or to follow the way that the transactions go through the system. So I've got a picture here looking at how we do that, and we could say that sitting on top of everything, you have your D app that's interacting maybe with a light node. They create a transaction. The transaction gets then passed off to a full node, and the full node is seeing this transaction that's come in. It's a brand new transaction, so it's going to publish it out to the network for the network to see. One of the people that's listening on the network will probably be a mining pool lead. The mining pool lead is going to see, hey, there's a brand new transaction. There looks like enough incentive for me to mine that transaction and add it to a block, so I'm going to do that. The mining pool lead will then go ahead and process the transaction and put it into a block and generate that block, do the proof of work or consensus upon that, and say, yep, this is a good block. And then it's going to publish that out to the world of Ethereum clients and distribute that out. So that's kind of the big picture of how a transaction goes from a single person out to the rest of the system. And as we begin to draw to a close, I will show that stack diagram one last time. Looking again, we've got the JSON RPC, our Ethereum core, there's networking happening, storage, and a wallet. I will stop now for questions and highlight that there's some other talks probably about this sort of length and this sort of style, which are coming, which will be talking about networking. So the networking talk is already prepared and done and coming soon, real soon. The consensus mechanism talk is scheduled for the Brisbane Ethereum group to be given in June. And so sometime after that, this kind of presentation will be created. And then sometime after June, I'm not sure the exact date, there's going to be a talk talking about the details of the Ethereum virtual machine as well. So I am going to pause for questions, which there might be none, which is completely appropriate.
Look, I've probably got an easy one for you, Merkle.
Yep.
If you go back one slide to the follow the money, or maybe it's 2 slides.
Yep.
So, I mean, ultimately, in that last piece of the puzzle, we see the Ethereum clients. They're actually getting delivered a block, which would go through their block processor and validation, and the EVM. The EVM would then execute whatever smart contracts were there, and the world state would then be updated in that final piece of the puzzle. Is that a reasonable understanding of what's happening?
Yep. Yep.
Yeah, terrific. Cool, Nicholas. Look, I think I'm kind of happy.
Cool. So I guess just a quick ad that producing this as part of Pegasus, the website's there, contact details for all the Pegasus, the ways of getting in touch with Pegasus are there. Or if you're inside Consensus, you can find me on Slack. I'm Rob Dawson. Cheers.